Assalamu alaikum. We continue on exploring data and how a certain way of quantifying the variation of the data distribution forms a fundamental concept in statistics on which one can base probabilities and assess significance of a measurement or a difference or a relation between variables. In the previous presentation, we've been through some of the methods of exploring data, either digital or visual, and been through things like the range and the interquartiles and the medians and the percentiles. In this presentation, we'll go through two other measures, the variance and the standard deviation, and the next presentation will go through the applications of the standard error of the mean. Both the variance and the standard deviation quantifies the spread of the observations around its average point, its central point, its mean. Starting with the variance, it averages the differences between each individual observation or measurement and the central point, the average point. And because some of these measures would be positive, i.e. the data would be more than the average or less than the average in other instances, rather than allowing the positive and the negative data to cancel each other, the differences are squared first and then divided by usually the number of the observations minus 1, because this is just a sample, or occasionally by the total number of observations if we have reasons to think that this is the whole population, like in a rare disease or a certain type of surgery. So the variance is the total differences between each point, each individual dot here, and the mean squared and then added together, and at the end we divide it with the number of the data minus 1. The standard deviation is simply the square root of the variance. In a normally distributed set of data, most of the observations will be in the middle. Precisely, just less than 70% of the data would be within one standard deviation above or below the mean, the central point. Precisely, this is 68% of the data would be expected to be within one standard deviation from the mean. If you take this a little bit further, then you to two standard deviations above and below the mean or the central point, then you can be pretty confident you have 95% of the data in there. Two standard deviations above or two standard deviations below the central point, the mean. Take it further to 3 standard deviations and you have more than 99% of the data within this. Any data out of these limits, like more than 3 standard deviations, will be extremely rare. Any observation more than 2 standard deviations away from the mean is also quite rare. It should be about 5% only of the data, half of them above and half of them below the mean. For the example of the pleomorphic adenomas here, if the mean is about 33 millimeters and the standard deviation is 10 millimeters, then we'd expect that most of the tumor sizes would be between 23 millimeters and 43 millimeters. Here you would have about 70% of the tumor sizes. But a tumor that measures more than, say, 53 millimeters would be rare. The chance of getting this tumor is less than 5%, and anything above 63 millimeters, that is 3 standard deviations from the mean, is extremely rare. And this forms the basis for quantifying the Z-score. The Z-score is a way of quantifying the difference between a certain tumor size, for example, and the average tumor size. So the Z-score equals the observation minus the mean divided by the standard deviation. If you have a tumor that measures 43 millimeters and the mean tumor size is 33 millimeters, the difference is 10 millimeters divided by the standard deviation, which is again 10, then the Z-score is 1. If the tumor size is 58 millimeters minus 33, the mean tumor size, this is 25 millimeters divided by 10, then the Z-score is 2.5. Remember that any Z-score more than 2 means that the size of the tumor would fall into the area of less than 5% of the population, so that's rare. And if the Z-score is more than 3, then it is less than 1 in 1,000 or so. It's extremely rare. And this is simply the way probabilities related to a certain measurement are deemed significant or not significant in relation to standard deviations. This is how the p-value is assessed. If a certain measurement is more than 2 standard deviations from the average point, from the mean, then it belongs to the 5% outside the limits of 2 standard deviations above and below the mean. Then it becomes rare or significant. If the measurement is less than 2 standard deviations from the mean, it belongs to the 95% that are within 2 standard deviations from the mean, and it is not significant. The same probability concept applies to a whole lot of statistical tests determining the p-value of a difference between two groups. Say the green and the violet groups are two different operations, the classic operation and the new technique. If the differences between the two groups in terms of the difference between the means of the two groups here in relation to the standard deviation is so small, as we can see here, then we are confident that there is no difference, no significant difference between the two groups. On the other hand, if the green group has much better results than the violet groups in terms of the differences between the two means divided by their standard deviations, then we can say that the differences are significant. By this, we come to the end on this presentation on some fundamental applications of the standard deviation. The next presentation will be on the confidence intervals. Assalamu alaikum.